Vou dar mute entretanto. Okay, hello everyone. I think we can start. My name is Filipa Castro. I'm part of Data Science for Social Goods Portugal. We normally call it DSSG because it's simpler. I want to welcome everyone to this first webinar of DSSG in partnership with NILG.AI. And I will start with a very quick presentation about our work. I think most of you already know that our main formula is to get beneficiaries together with volunteers. These beneficiaries can be charities, NGOs, or even institutions from the public administration. They normally have some data, and then they normally ask us to solve some kind of problem that always has a social for good purpose. And our volunteers may be data scientists, data enthusiasts, but they can also be developers or even designers to help in the projects. Normally, these projects last for 3 to 6 months. They are not complex. The main goal here is that we have a deliverable, and this deliverable has a high impact in this beneficiary and in society in general. So regarding our projects, the first one was with the Rotaract, and it's already finished. This was a exploratory analysis of the data regarding a fundraising campaign against cancer, where we delivered an interactive report to help plan future campaigns. At the moment, we are running a project with the Associação Zoófila Portuguesa, which is like a public vet hospital. And the goal here is to use some descriptive analytics and clustering methods to try to optimize the time the client spends waiting for appointments and treatments in the clinic. At the moment, we have a project on hold with VOST PT because of the COVID-19 pandemic. This is on hold, but we expect it to restart very soon. The goal here is to measure and characterize the impact of the Leslie hurricane. Basically, they already have some impact measurements, but they want to cross this information with some other sources like news to better characterize this and plan for future disasters. And around 3 weeks, 1 month ago, we started another project with Caixa. They have a magazine and they have some sellers, which normally are people with low income. And they give this magazine to the sellers who can sell the magazine and then use this extra income to pay their rent or to pay for their food. And what we want to do is to analyze their data about the sellers and then to build some kind of storytelling story to raise awareness for what they do. So as a volunteer, as you may know, you can always help in this kind of projects. You can check the projects that we currently have and that I talked about in our tab projects in our website. But we also have some other mini projects. These are available on our GitHub page. And for now, we have around 5 mini projects, which are all related to our COVID repository, but soon, who knows, we'll have other projects there. You can always participate in events like this one and help us share these events. You can check our social networks to know more about this. And now we also have another initiative, what you call the Data for Good Ambassador. So here you can bridge the gap between us, the SSG, and your organization or your company. And imagine you work in a company that might be interested in supporting the SSG. They can be our tech partners where they provide us with some services or some solutions or even data. They can sponsor our events. They can be the patrons of a particular project. For instance, they can provide us with some space for the team to meet. They can cover some general expenses, or they can also be our knowledge partners, like NILG.AI, and provide our volunteers with some training or workshops like this one. So thank you so much for being a DSSG volunteer and for being here today. You can always follow our social media to get to know about our initiatives. And now I want to let Paulo talk about the theme of today. I want also to remind everyone that during the talk you can write some questions in the comments section. And we will then select some of them, or if there's time, Paulo will answer to all of them. So now, Paulo, welcome to the stage.
I'm sharing the screen. I don't know if you can see it already.
Not yet, I think.
I think I have to put the screen on stage. Yeah, it's working, I think. Yep.
Yeah.
Okay, so let this load. Okay, so hello everyone. My name is Paulo Maia. I've been a data scientist at NILGAI since mid-August, a few months after I finished my graduation in bioengineering at the Faculty of Engineering of University of Porto. And the title of my talk is Applying Geospatial Data for Machine Learning with a focus on social good. And besides being a data scientist at NILGAI, I'm also a member of the lead team for the SSG in the communications department. So what is NILGAI? We are a consulting company in artificial intelligence, and our main goal is to help small to large companies make informed decisions, promoting efficient opportunity handling using the data they have available, or even help them establish good data-driven businesses. But our most different point from other projects we see is that we try to adapt the technology of the customers to our business. So we don't sell off-the-shelf solutions that they can use. We actually try to understand their business end to end, see at which points of the value chain we can make some impact, and then propose the best ways of doing so, so they can integrate the data they generate in their daily decisions. Regarding our network, we have worked with clients all across the globe in several industries like healthcare, telecommunications, fintech, chemistry, utilities, and marketing. So we have knowledge in all of these industries and in several use cases. And this is also possible because we have a network of partners which allow us to get new projects and to have some exposure to new clients and employees. And this is our team. We are a very small team contained of around 6 people, 5 data scientists. I'm this guy over here, as you can tell. And so starting with the talk, my first chapter is about spatio-temporal data types. So what kind of data can we expect when we want to treat geospatial problems? Starting with the definition, what is actually spatio-temporal data? So it is defined as data containing both a spatial and a temporal component, and giving some practical examples, remote sensing data, the route taken by a transport, like a GPS following a bus or a taxi. Also the measurements done by a sensor in the street, like a radar. Medical imaging is also a type of spatial temporal data, but only some kinds of medical imaging, like the fMRI exam, which has a component containing time and also the imaging part. And of course, videos are also a kind of spatial temporal data because you have the pixels in the video with the temporal component. And these kinds of data is applicable in several domains, such as environment, climate, public safety, and human mobility. And why should we treat spatial temporal data differently than all the other sources of data, like static data? So traditional machine learning methods based on tabular data, like random forest or logistic regressions, etc., don't work as well when we are treating spatial temporal data, because spatial temporal data is in continuous space, and these tabular methods treat data in a discrete way. And the patterns of this type of data typically contain spatial and temporal properties, which are hard to capture by traditional methods. And related with this, the data samples are not independently generated, so we have an autocorrelation both spatially and temporally between the samples. For instance, if we are analyzing part of the data in a given region of a country, the closer we are to that region, the more correlated the data samples will be. And traditional methods are also very reliant on doing manual feature engineering, which is kind of hard to do in spatial temporal data when you don't know the optimal features to extract, and it's very domain dependent, and sometimes it's best to let the machine decide for us how to extract the features. So starting with the description of data types we can find, we can find event data, which are discrete events occurring at point, location, and times. For instance, crime events, traffic accidents, disease outbreaks, social events and trending topics, or even data from the civil protection. And this is typically described as a tuple with three elements, which are the event type, the location, and the time. And here I have a public data source specific from Portugal, which is the civil protection data. You can extract this data using an API. I think it's actually VOST who has an API to extract this type of data. And here you have the occurrence of incidents, which is an event type, like the nature of the incident is an event type. They occur at a given location and at a given time. Of course, you also have some extra features you can add. The second data type I want to talk about is the trajectory. Trajectory type denotes the paths traced by bodies moving in space over time, like a moving route of transports, such as a bus. And this is typically collected by sensors in a moving object. And you represent this type of data by a sequence, LI-TI, where LI is the location and TI is the time. So you follow a given object throughout all these locations, L1 to L5, at different time points. An example of public data sources you can find with this type is the data from Carris, containing the route of bus in Lisbon. Another data type you can find is point reference data, which is the measurement of a continuous spatial temporal field, like temperature, vegetation, or population, over a set of moving reference points, both in space and time. And the practical example is weather balloons, which move throughout the atmosphere and measure certain parameters, such as pressure and temperature, throughout the time. And this is typically represented as a heat map, or more specifically as a tuple Ri, Li, Ti with a measurement value m, where Ri is the sensor, here represented in white, Li is the location, and Ti is the time. Here in this map, you have two different time points. The sensor location moves throughout these time points, and you measure a given value. Another data type is raster data, which is similar to the previous data type. So here we consider spatial temporal fields which are recorded at fixed locations and time points, while the previous data type had changing locations. And examples of data we can measure of this type is air quality data, traffic flow, car speed, etc. And we typically represent this in the form of a matrix. So for m fixed locations and n timestamps, we represent this as a matrix or an image. In this example here, we have in the x-axis the IDs of the road links, and in the y-axis the hour of the day. And this is measuring traffic flow. So the higher the intensity of the pixels, the higher the traffic flow is in this given road link. An example of a public data source you can find is measurement of air quality, which is linked here below. We'll send the slides so you can check. It's the QualR website. So how can we treat these types of data? First, it's important to represent this data in a way that the machines can understand. In the literature, I found these three groups of ways we can represent the data. So we start with a data type, which is the way we collect the raw data. And then we have to associate each of these data types with a data instance. A data instance is something that has an associated label value. For instance, if we want to determine the number of people which will be in a certain location at a given time, our data instance is the number of people in that location in that timestamp. Something we can then use to feed our models and to train our models and to validate them. And there are several ways we can do this. We can represent this type of data as points, trajectories, time series, spatial maps, and ST rasters. I'm not going to spend too much time in this because it's better to just show examples later. After having a data instance, we need to represent this in a way that our models can actually use this data to learn. And here I'm not talking about classical models, but I'm talking about deep learning models, which are typically the state of the art for this kind of problems, because they can extract the features manually and determine the correlations both spatially and temporally automatically. And here we can represent data as sequences, as graphs, as 2D matrices, or 3D tensors. But I'd like to say that there is not a best way of representing spatial temporal data. And here I have two different use cases, which are traffic flow prediction, where we can represent data as a traffic flow graph containing at each node the speed of the cars or something at that location. Or we can represent as a cell region level traffic flow matrix, where we divide a map of the city into grids, and for a certain timestamp, we plot as the intensity value a value which is correlated with the speed at that location. So there are advantages and disadvantages at having these types of representations. When we have a graph, we don't consider an Euclidean distance between points. And when we have a 2D matrix, we may lose some of the 3D correlation, meaning in time or both between X and Y. So the best thing to do is to just try both. Another use case I have here is a problem with wind forecasting at a given location and time. And we can represent sensor data as a 2D matrix containing the wind intensity, and meaning the location and the time step. So this is an image. And we can also represent this as a 3D tensor containing the row region sensor ID, the column region sensor ID, and the timestamp. And with the 2D representation, we lose the correlation in the extra dimension that we added here. In the literature, there are several modeling approaches for these types of data. I'm not going to spend too much time describing them, but the most important thing is that recurrent neural networks are mostly used for treating trajectories and time series. Convolutional neural networks are typical in map-like data, like spatial maps or ST rasters, because this is a model that is typically used for images. And graph CNNs are typically used for graph data. So regarding the pipeline for most spatial temporal data problems, I already talked a bit in the previous slides, but we start from having raw spatial temporal data, construct a data instance which has an associated label, and then pre-process this data to have a given representation to which we can feed to our models, to our deep learning models, and this will be trained for a certain task, like prediction, representation, generation, classification. Regarding the distribution of these types of tasks in the literature, most tasks are regarding prediction, which are problems like predicting the future observations of a spatial temporal data based on its historical data, like wind forecasting, as I said before. A very big slice also is in representation tasks, which are focused on learning the abstract representations of the input data and then facilitate other downstream data tasks. This is like clustering the data or finding a representation using an autoencoder. Also, we have classification problems, whose goal is to separate geospatial data in classes. An example is like using the functional magnetic resonance imaging for disease classification. And we also have estimation tasks, which are based on information inference. And the practical example is estimating air quality in a given region of the country, having only the data points for the measurement centrals, which are in very specific points in the country. Another point I would like to talk about is the way to evaluate these models. This isn't typically mentioned in the review articles, but it's something that we at NILGAI have covered in a past blog post you have here in the bottom, which is how do you partition your train and test data so you can make sure that your model generalizes well when seeing new data. And you can do this in 3 different ways. You can do a spatial partition, where you validate the model in train and test in different spatial locations. You can do a temporal partition, where you train the model in a given timestamp and you validate it in a timestamp in the future. So you don't have data leakage of the information that can occur in the future. Or you can combine both and do a spatial and temporal partition of your training and test data set. In the blog post, we covered this specifically for fraud detection in the utilities department, but this is applicable in several geospatial problems. Okay, now I'm going to focus a bit on some use cases I found in the literature. I think this is especially important so you can find some inspiration and try to apply this in Portuguese public data. The first thing I would like to talk about is traffic accident count prediction. And the goal of this project is to improve transportation, public safety, and safe routing. Regarding the challenges of this type of problem, the occurrence of accidents both in space and time is something that is very rare. Obviously, and gladly, you don't have accidents every time in every place. So this is a very sparse type of data. And you have also a lot of spatial heterogeneity, meaning that rural and urban environments have different accident factors. Like in the cities, the traffic might be the most important risk factor, but in rural environments where the road quality is not so high, you may be more concerned with weather conditions, for instance. In the literature, this is commonly formulated as a classification or regression problem. And the classification problem is the first type. It's the answer to the question, will there be an accident in a given location and time? And the regression problem is the accident count in a given location and time. And in this paper, their objective is actually to determine the accident count in a given location and time. So they have the ground truth, which is the actual occurrence of accidents in each region and in this day, and they try to predict it. Regarding the data sources used in this article, as a target for training the model, they used crash data, officially gotten from the government. As auxiliary data, the authors used road networks for understanding the shape of the road networks. Like they calculated features related with the number of intersections, the speed, the average and the maximum speed at these networks, etc. And as features for the model to learn how to predict the number of accidents, the authors used satellite images, which can be used as a way of understanding like how the terrain is, how the road is. They also use traffic camera data for counting the typical number of vehicles in a given area, rainfall data for understanding how the weather was when the accident occurred. And these called RWIS stations, which is a specific nomenclature for America, that are stations that measure temperature and wind at given regions, which are plotted in this map as red. And how did they formulate this problem? Well, for getting our data instances, the map was partitioned in a square spatial grid, which I'm here naming as S, containing elements S sub y. And these data sources I mentioned here, these features, were saved as a 3D tensor, meaning the value in a given x, y position at a given time of these features. And then the map was masked according to the road networks, meaning that we only want predictions where we actually have roads. We don't want our model to give an estimation of an accident which occurs outside a road. And so the target in this problem is to predict the total number of accidents in a given time window for a given cell S sub y. Regarding the model used by the authors, they used a convolutional LSTM cell for automatically extracting features from data. This type of models can be applied for 3D tensors data, and we have a two-dimensional matrix here, this matrix H and X, which is the features. I'm not going to go into too much detail. And for this model, the authors used the last 7 days for training the model and try to predict the next 7 days. This amount of data, like the 7 days, was chosen because they are analyzing human activity, which typically has a weekly pattern, and this was the best window that they found to correlate with the human pattern. And the first 7 years in this article were used for training the model, and the last 7 years for testing, meaning they did a partition by time, so the model did not have information regarding the future before they had actual access to it. And here they trained something that they called a regional convolutional LSTM network. And why is this a regional network? Well, as I said before, the issue of spatial heterogeneity is very big in these types of problems. And for solving this, the authors learned a model for each region. So they had the whole map in which they wanted to predict the accident count. They determined a given window size, and they learned the model for each window, meaning that each model had to learn specific patterns for a certain road network and soil type. So we can have rural areas, urban areas, or mixed areas. And the focus of the authors was that they could then ensemble all the predictions, meaning combine them, and then create a better model for this. I won't show the results here because I don't think it's very interesting, but the link is here below. So the second paper that I want to talk about is fair demand prediction in mobility systems. The motivation for this is that new mobility systems, such as bike sharing, offer affordable transport options for citizens. However, the most common demand prediction models do not actually deal with the social disparities, meaning that less demand in an area for typical models means less interest. But this is not real. It may mean an area which has less disadvantaged groups. In terms of implementation, this paper is very similar to the previous one. So they have external features like the weather and the road networks. And as a label, they have the amount of bikes requested in a certain area. But there is a different thing implemented here. They implement some fairness metrics for ensuring that the model tries to tackle this issue of social disparities. So the authors determine a set of sensitive attributes such as education, race, and age, and implement a fairness regularizer for obtaining equitable demand prediction, which I'll describe next. So how can we incorporate fairness in these types of approaches? There are several ways of incorporating fairness, but specifically in this article, the authors consider that individuals of different groups must have access to the same resource. And they implement these two sets of rules, meaning group fairness. Group fairness means that the disadvantaged group must experience similar predicted outcomes as the advantaged group. And also vertical equity means that transportation policies must favor the disadvantaged group, and we will then have a balance of these two approaches. And both these fairness metrics measure the gap between mean demand per capita across two groups over a certain period of time. So we want the demand to be dependent not on these sensitive attributes like the socioeconomic factors, but on the population density in a given region. And the authors define these two fairness gaps, which are region-based fairness gap, meaning that each geographic region has a categorical label, such as Caucasian, and the individual-based fairness gap, meaning that the group label is numeric. So a region has a certain percentage of Caucasian people. In a bit more detail, they do this by modifying the loss function used to train the model and adding the following terms. A first term called the regression loss, which penalizes when the model makes wrong predictions in terms of the demand value itself, which is the mean absolute error you all know. They have a region fairness loss, which penalizes the model when the demand per capita in a region which contains both groups, advantaged and disadvantaged, is not the same. And the third loss is the individual fairness loss, which penalizes the model when the demand per capita in a region containing both groups does not favor the disadvantaged group. So as I said before, they have the weights containing the percentage of each people in the region. And the disadvantaged group is the group which has less weight in this region. I also don't have results in this paper. This was a conference paper I found, but the results are here below. I tried to search to see if they actually implemented this in real life, but I think this was only an applied research paper, unfortunately. But hopefully someone will implement this one day. So the last paper I want to talk about is a problem of city inflow and outflow prediction. And why is this important? Because crowd flow prediction allows us to manage both traffic and public safety. And we can measure the crowd flow by several factors, such as the number of pedestrians, cars, and people traveling on public transportation systems, like only one of them or all of them, depending on the amount of data we have. Specifically, this article uses GPS data for measuring the number of pedestrians in a given area. And this is a very challenging problem due to several factors. So we have spatial dependencies, meaning that the outflow in a region affects the inflow in another region. In this example here, people go from R1 to R2, but the amount of people present in R2 will affect the outflow from R2 and the inflow in R3. There are also temporal dependencies, meaning that if we have like a traffic congestion at 8 a.m., this will affect the typical traffic flow at 9 a.m. And people's routines also change throughout the year. Like in summer and in winter, people have different kinds of routines in terms of going to work, the daily commutes. And this is very affected by external factors, such as the weather. Like when it's raining, there's typically more traffic. Starting by how the authors define the problem, similar to the previous works I presented, they divide the map into grids with a fixed grid size, and then calculate an inflow and outflow to the matrix for each time step. So for each grid point, they have the number of people which left that point at a given time and which entered. And the goal of this project is, given the historical observations up to the point t-1, they want to predict the count of inflow and outflow at point t. I'm going to enter in a bit more detail regarding the architecture here, but not very much because we have a very diverse crowd in terms of formation. The link is here below, as always. So, as in the previous papers, they also use a multi-model approach containing context features like the weather, the day of the week, whether it's a weekend or a holiday or even a game day. They extract features from context, like they do a manual feature engineering, and then we have this block of external features, which I'll come back to later. Regarding the crowd flow data, this is measured as a 2D map with two channels containing one channel containing the inflow, another channel containing the outflow, and we have these images throughout the time. And the authors needed to find a way to monitor the change in people's behavior throughout the time. So they divided this in three blocks, which are the closeness features, the period features, and the trend features. So closeness features is the type of information that we need to have when which is very close to the time step we are predicting. So here in blue, it is something which has a very high frequency, meaning we want a lot of data points in the recent area for understanding what exactly is happening at this time point and how will it impact the future. Then they also extract this block of features called the near features, which are best used for understanding the period of people's behaviors. Like on the weekends, there's less traffic at 8 a.m. because people don't have to go to work. At Monday, there's more traffic. And by extracting near features, we can get this. And then the last block of features is distant features, which are used mostly for modeling trends, like for things that occur throughout the months, like in the changes in traffic in winter and in summer. And the way the authors do this is by having all this crowd flow data and the historical data, as I said before, and then applying subsampling with different sampling rates depending on the type of data, on the group they want to extract data from, one of these three: closeness, period, or trend. And in the distance data, the sampling frequency is smaller, meaning we want more spaced images. And in the recent group, we want more high frequency sampling rate. And then the authors need to combine all this. So they have a multi-layer perceptor here, which joins all the features. And they then calculate a loss function, which is something like a mean absolute error or a mean squared error, which penalizes the model when it makes a mistake in estimating the number of people in that region. So in a bit more detail regarding the architecture, the authors use several convolutional layers in this image-like data, and they stack these types of layers and try to interpret their meaning. And if we have only a single layer, we could not get all types of correlations between different spatial regions of the city. Meaning, if you have a given inflow and outflow at a region, that region may be connected to another exit of the city, and the outflow will in the exit will be correlated with the inflow at the other entry. So by stacking several convolutional layers, the authors say that it is possible to have to extract these types of correlations at several spatial sizes, meaning that each convolutional layer learns a different type of feature. So some are more detailed and more high level, and others are very general and represent the average behavior of people in a region. And for learning this, they also use an architecture based on the ResNet network. So they call this architecture the spatial temporal ResNet. And they use these skip connections for learning the difference between the output at a time step and in the previous time step. So the objective here is that we start with the baseline information and try to learn what will be different regarding our baseline. And I would like to conclude by saying that there are many ways that spatial temporal data can be used for AI applications. As I said before, there is not a best way of representing data and not a best model to apply. And from what I found, there is not much, if any, research being done using open data in Portugal. So I challenge you to start doing this. And here are two sources in which you can find data, which are Central de Dados and Dados Abertos. And I'm sure the SHG will actually give you some exposure if you want to do these kinds of projects, and perhaps help you find motivated volunteers for doing so. As Felipe mentioned, they and we have the mini projects. We don't have a mini project yet using geospatial data, but maybe we can do it in the future depending on your interest. And that's it. We can go for the questions now. Thank you for your attention.
Thanks, Paulo, for the great presentation. Yes, I think we can move to the questions. For now, I think we just have one, but I invite everyone to add other questions in the comments section. So the one we have is from Pedro Oliveira, and he is asking if the papers you mentioned. I think we will share the slides later, so then everyone can check the papers. But he is asking if these papers are not implemented yet. I think you mentioned one, which is not. But the other ones, they have some results, right?
Yeah, I mentioned they are not implemented in real life. I'm actually not sure if they have code approaches, like they have public code on GitHub available. I can check that later, but I think one of them actually had code publicly available. I'm not sure which one, but sadly, this was only all these works were only done for specific conferences, from what I found. But some of them are recent, like 2019, 2020. So maybe people still haven't had the time to realize the importance of their work and to implement it.
Okay, I don't know if there are more questions. I would like to ask you one more regarding NILG.AI. So you mentioned that the blog post that you have is about fraud detection, I think. Yeah. My question was, is that if you have other use cases where you used some of these approaches, or if there is any use case that maybe it's not directly to social good, but if there are some use cases that you see in your work in NILGAI that you think you could easily adapt for some ideas for social good.
Yeah, we have worked a bit in this type of use cases, but not in the social good domain. So we work with a major telco in Portugal, which is NOS, and NOS is very rich in geospatial data. I cannot directly refer what we worked on, but there are several use cases we can use based on the presence of people in the given region, for instance, like not only customers, but salesmen. And let me think about other possible use cases. Well, recently we have been working with medical imaging, and some of medical imaging can be represented as like a spatial a video. Like if you have several exams from the same patient, you can represent it as spatial temporal data. It's a possible use case. And we have been working with video use cases, but it's a bit different from the typical spatial temporal data mentioned in this paper. Yeah, but we're always eager to new projects in this area. So if there's someone in the audience which has a problem to solve in this area, just contact us.
Okay, but meanwhile, I think we have some more questions. So Sergio Nunes is asking if you know any project that tries to predict the actual location of something.
By location, you mean where a certain object will be present in the future, like trajectory forecasting? I found some in the literature. I don't recall the exact example. I don't know if it was related with public transportation systems because they follow a typical route. Maybe I think actually the example I saw was related with seeing if a certain transport would be at that position. So if it would follow the predicted, the theoretical schedule. But I'm sure there are a lot more examples. I can't recall one for now. Maybe in a few minutes I'll do. But I have linked one of the review papers I used to make this presentation, and there are a lot of possible use cases there. So you can check it also. Sergio
Uh,
clarified, or where it is right now. This depends on the type of problem. If you have like an estimation problem, as I classify them, you can probably estimate where a given car. Yeah, let's focus on a practical example. So if you want to measure the position of a car based only on the traffic flow data recorded in the sensors at fixed positions, you can probably make an estimation based on the speed of the other cars and the speed of the car you're trying to measure when it passed the certain road links in which you have sensors. I think that's probably the simplest use case I can remember, and this will depend on traffic, on the average road speed the person passes throughout the time. This could probably be good for understanding if people are going above the speed limit. But in some use cases, you actually have access to the location constantly, like by GPS or by satellite. So you can treat this problem in a different way.
yeah. And we have one last question from someone that you might know, Calvin, which is how to combine geospatial and tabular data.
Okay, so Kelvin is the CEO of NILGAI for those who don't know. And the combination of this type of data can be done in several ways. The simplest way is by having neural networks which have several inputs. And I think maybe I can share an example. Let me see if I can find a good graph in the paper. I think I had one. Yeah, I'll share the screen again. This was not combined, or I will have it in the backup slides. uh, I think you can see. No? Okay, so this is a problem where that question was actually posed. We have groups of features which are called the static features and the dynamic features. And using neural networks, we can combine these into two streams of data. For the static features, we use simpler networks like fully connected neural networks. And for the dynamic features, we can use networks which consider the automatic extraction of correlations between space and time, as I said before, like CNNs or LSTMs. And then we can combine this in several approaches. We can do a simple concatenation of these features. We can do like an attention-based pooling, which is done here. I don't know exactly how they did it. And our final output will then be a layer which combines these two types of data sources and tries to predict something. Just a comment, this is probably a mistake because meteorological data is not static. And in a bit more of a curiosity, you can actually apply some strategies to multimodal data in case you won't have access to all sources of data at all times. this is not a good example, but if you only have access to like the right stream here for 30% of your data set, when training the model, we recommend you to apply dropout in the input, and this dropout is in the form of, in the training set, manually or automatically removing some of the data sources here, so that the model learns how to predict in the absence of some of these data sources. This is something that maybe we'll cover in a later blog post at NILGAI, because we have treated some of these issues internally.
Okay, I think that Sergio who asked about the location, predicting the location of something, he gave now an example about parking meters, but I think parking meters normally they don't depend, or they don't change location with time, but maybe we can use spatial, temporal and data like the traffic in a certain place and try to predict where this maybe.
Yeah, I think I understand the issue. Well, you will probably, for this issue, you will probably be good by using like satellite data from Google Earth, because from the 30% of parking meters you have, you can probably train a classifier for object detection that determines the location in a given image of parking meters, or just a binary classification if they are present or not. And then you could apply this to the other 70%. Since you probably have low amount of labeled data, you can use approaches based on semi-supervised learning, for instance, which uses the fact that you only have labels for a subset of your data set, but uses the structure of all images for trying to understand like what are the best features to automatically extract. I don't know if this was what you wanted to exactly ask. Maybe you can clarify. If not, since no one else is asking questions and we still have 3 minutes. But I'd say with only sensor data, you will have good information. With only satellite data, sorry, you will have sufficient information for this problem.
Yeah, I also left our email from the SSG, and then if you want to share yours from NILGAI, and if anyone wants to send some additional questions we didn't have the time to address here, you can send them to us. And then we'll also share the presentation with all of you. Yeah. Okay, so thank you everyone that was here. I would also like to thank to NILGAI and Paulo for your time and for your great presentation. I think Kelvin is also here, so thanks for being our first knowledge partner. This was our first event, but we will have future webinars. I think we have one additional question here from Luis Teixeira, I think it's Professor Luis Teixeira,
Yeah,
which is yes, nice which is asking that regarding your last use case, is asking if the subsampling is fixed, and it kind of reminds him of the slow fast model for activity recognition in videos.
Sadly, I don't know the response. I can try to check quickly. This is reminding me of college. I have the file here. I actually don't remember if they fixed a sampling size.
Maybe you can also share then the link to this paper.
When I read it, it was actually not clear how they did this from the image. I thought that they manually determined the sampling rate. They mention a parameter, which is like the shifting size, and I assumed that they did it manually. I'm not sure. Yeah, but I'll share the paper.
Okay, so thank you everyone, and stay tuned with our social networks and our newsletter, and we'll have future webinars also in partnership with NILGAI. And I think we'll end the broadcast here. Thank you.
Okay, thank you.